Around the world, climate changes are happening faster than ever due to the increasing amount of CO2 in the atmosphere. Temperatures are rising, extreme weather are starting to occur more frequently, rainfall patterns are shifting, ice and snow are melting, and the global mean sea level is rising. One of the biggest contributors to the climate changes is the building industry, which is responsible for approximately 40% of the total climate impact in the world. Consequently, the effort on reducing especially the CO2 emission from building materials and operational energy has been intensified. As part of the building industry, Airmaster wants to contribute to this effort and has consequently asked Mo Consulting Engineers how to address this as a company producing air handling units. One of the methods to deal with the global aim of reducing emissions of CO2 is to look at buildings and building materials in a life cycle perspective and assess the environmental impact through every life cycle stage. In other words, making a life cycle assessment. A life cycle assessment is the most reliable and complete method to evaluate the environmental impact of any product or building as a whole. The method considers every life cycle stage from the raw material extraction to the use stage and at last the end of life stage. Usually when considering buildings, the life cycle assessment is made for a consideration period of 50 years. This means that the energy consumption for all 50 years are included in the assessment, as well as replacement of materials, which has a shorter lifetime than the consideration period. In the end, when evaluating the results of a life cycle assessment, the environmental impact is assessed for a wide range of environmental impact categories, such as global warming potential, acidification potential, and use of primary energy. However, due to the focus on reducing the climate changes, the most applied impact category is the global warming potential, expressed as the total amount of CO2 emitted to the atmosphere. Even though focused most often is on the global warming potential, the wide range of impact categories are useful when it comes to the increasing number of certification schemes, which all evaluate sustainability in a more holistic approach. For example, when looking at the 17 Sustainable Development Goals defined by the United Nations. Here, the method of an LCA can be used to address 5 of the 17 goals. To be specific, an LCA can be used to ensure clean drinking water and life in the ocean, defined in goal number 6 and 14. LCA can also be used to reduce the primary energy consumption, defined in goal number 7 and 12, and of course to minimize the CO2 emission to the air, defined in goal number 13. Besides being useful in relation to the Sustainable Development Goals, LCA is also introduced as a requirement in the new sustainability class in Denmark. This sustainability class has 9 different requirements which all should be fulfilled. One of the requirements is to make an LCA on building level. This LCA should include all building materials, transportation, waste, operational energy and demolition of the building after its lifetime. For now, the sustainability class is optional and in a 2-year test phase. However, it is expected to be part of the national building regulations after the test phase. At this time, a maximum value for the environmental impact is also expected to be introduced. In addition to the sustainability class, LCA is also included in the GGNB certification. Here, the LCA-related criteria accounts for around 10% of the total possible score. Points are awarded for making an LCA in the early design phase and for using LCA as an optimizing process to reduce the total embodied CO2 in the building. The requirements for the LCA in the GGNB certification comply with the Danish sustainability class. However, where the sustainability class does not have an upper limit for the environmental impact, GGNB relates the environmental impact to a reference building in order to evaluate the results. As part of GGNB, life cycle assessments on building level have been carried out for more than 10 years. Nevertheless, the assessments most often do not, or to a limited extent, include the installations for the building operation such as plumbing, heating and ventilations. Preliminary analysis, however, indicates that a significant share of the total embodied CO2 in the buildings is caused by installations and that they may not be left out of the assessment. Therefore, Airmaster and Mo has made a case study of the environmental impact of two different ventilation systems on a Danish primary school from 1968. The case study is based on a building section containing 31 classrooms where decentralized Airmaster units have been installed during refurbishment. This scenario is compared to a fictitious scenario where the decentralized ventilation system is changed to a centralized VAV system. On this slide, the two different ventilation systems are compared next to each other. Both systems have the same working hours and airflow to secure a maximum CO2 content of 1000 ppm in the indoor air. So the big difference is the distribution system. For the decentralized system with the Airmaster units, no distribution ducts are needed at all as the air handling units are installed directly in the rooms. The centralized system, on the other hand, needs distribution ducts, dampers, diffusers and so on to work, and this has a big influence on especially the SFP value and hereby the energy consumption. To give an overview, this page illustrates a floor plan of the two different ventilation systems. The plan to the right is the actual refurbished rooms, and the plan to the left is how the fictitious ventilation scenario is composed. Because the rooms in the decentralized scenario are uneven distributed in the building, the distribution of the rooms is changed a bit in the centralized scenario. However, the total number of rooms are unchanged. If we start by looking at the quantities of the materials that are part of the centralized ventilation system, we can see that there's a large number of ducts and fittings and that the unit itself weighs about 3.5 tons. When added together, the centralized ventilation system has a total weight of 15 tons. If the ducts and the air handling unit then are placed on top of the roof because there's limited space on the inside of the building envelope, insulation must be added to the material list, and then we get a total weight about 18 tons. On the other hand, if we look at the decentralized ventilation system, there are only 31 Airmaster units and a few ducts for inlet and exhaust through the exterior wall. The total weight of this system adds up to just over 9 tons. This means that if we compare the decentralized system with the centralized ventilation system placed on the roof, there's a potential saving of 50% in terms of weight. So now that we have the quantities of all materials for both ventilation systems, we can start making the LCA. And for this assessment, the included life cycle stages are the ones that are part of the Danish sustainability class. This means that the production and construction stages A1 to A5 are included, as well as the use stage B4 and B6, and in the end of life scenario C3 and C4. The consideration period is chosen to be 25 years, as this is the service life of an air handling unit, but since no of the included materials in the assessment has a shorter lifetime than 25 years, no replacements are necessary. For each material in the assessment, the specific quantity is multiplied by the matching material data. As this is a general assessment with no knowledge of the specific materials, generic material data from the German database Ökobau is used. The data for each material contains information of the environmental impact, and in this case, the amount of CO2 embodied in each material. As generic material data are chosen, the LCA is not product-specific, but a general comparison of two ventilation systems with the listed materials. We start by looking at the results for the centralized air handling unit itself. For fun, the results are compared to generic data for two different units from the Ökobau database. These data are often used if you are making an LCA on building level. As seen on the PowerPoint, it's possible to choose between a unit with a maximum airflow of 10,000 cubic meters per hour and a unit with a maximum airflow of 30,000 cubic meters per hour. However, when we're looking at the weight of the units, something is wrong. The unit with the maximum airflow of 30,000 cubic meters per hour only weighs about 170 kilos, and the supposed smaller unit weighs about 700 kilos. If we then look at the actual weight of an air handling unit with a maximum capacity of 30,000 cubic meters per hour, the total weight is about 3.5 tons. The embodied CO2 in this unit is 12 tons of CO2, which is more than 4 times the CO2 emission from the generic unit with the capacity of 10,000 cubic meters per hour. This number does not encourage to make an accurate LCA of an air handling unit, but on the other hand, it shows that the generic data are completely wrong for these products and that new and more reliable data are needed. If we then look at the entire ventilation system, this case study has compared a centralized ventilation system with a decentralized ventilation system. Each system has 2 variations. One centralized solution is without insulation and one is with insulation, as this solution is assumed to be installed on the roof and hereby insulated against heat loss. As for the decentralized system, the study has compared a solution where the decentralized air handling unit works alone without inlet diffusers and one solution where the air is supplied to the room through inlet diffusers. As seen on the chart, there's a potential saving of 52% if a decentralized ventilation system without inlet diffusers is chosen instead of a centralized ventilation system installed on the roof. If the inlet diffusers are included in the decentralized ventilation system, the saving potential is 42%. Besides the saving potential, the study shows that the decentralized air handling units make up a larger share of the total CO2 emission for the overall system. But because there are no distribution ducts, the total CO2 footprint is much lower than for the centralized ventilation system. Furthermore, as the amount of material is much smaller for the decentralized system, the CO2 emission related to the transportation is also much lower. And the same picture is seen on the use stage, where the low SFP value leads to a low energy consumption and hereby a low CO2 emission. Finally, if we look at a building as a whole, the chart on this slide shows how large a share the ventilation accounts for. For this analysis, a reference value for a concrete office building have been used and added to the previous results. As seen on the chart, the centralized ventilation system accounts for about 16 to 18% of the total CO2 emission, depending on whether it's with or without insulation. For the decentralized ventilation system, the share is 10 to 12%. Based on these numbers, the study highlights the importance of including the ventilation and other installation for the building operation in the life cycle assessment of buildings. They make up a significant share of the total embodied CO2 and must not be left out of the assessment. However, the current available data are insufficient or not existing. If an upper limit for the environmental impact of a building is introduced in the building regulation in 2 years, we need to put a significant amount of work into preparing reliable data. Right now, the Danish Climate Partnership proposes a maximum value of 8.5 kilo CO2 per square meter per year, but as seen on the chart, all scenarios are above 9 and approaching 10 kilo CO2 per square meter per year. To conclude, even though the presented case study is not product specific, the results of the study show a significant saving potential when choosing a decentralized ventilation system. Depending on the specific solution, the CO2 emission can be reduced by half over a period of 25 years compared to a centralized VAV system.